in the so-called graveyard orbits, and maybe someday people will learn to recycle in space, and they can use this, let's say, raw material for some kind of reutilization. So the concept of operations are going as follows. We have to detect, I already mentioned, we have to detect the debris, we have to observe it. So we use the so-called observer satellite. This satellite is equipped with two LiDAR sensors. LiDARs are like a radar, but it's not using radio waves, it's using light. It's like a scanning laser. So, because in space you don't have atmosphere, you don't have perturbations, you don't have any disturbance, or it's quite minor, you can afford of having LiDARs with massive coverage and range. And right now we're showing one, for example, one chosen orbit for where the observer should go around Earth. This is a near polar orbit between 82 and 85 degrees inclination. The polar orbits is where the polar regions is where all the orbits intersect. So you have the biggest chance to get hit there in this region where the risk is high. So according to ESA studies and NASA studies, the most polluted orbits are around 800 kilometers and 1400 kilometers. So we put the observer pretty much in the middle. We equip the observer with two LiDARs facing the opposite direction, and the observer can start scanning and mapping all the debris. So if you 400 kilometers is not that small length, it's not that small coverage. So if we draw this to scale, one observer can cover like these two red orbits around Earth. So this picture actually is to scale. After we get the data, we send it to the ground stations. Let's say we work with them, we analyze them, we make this map. We can make predictions where there is a certain cloud of debris. So we can plan the aggregation mission. We can plan to go there and get it. So the second type of satellite we have is the aggregator. So this is just a simple model of what the aggregator actually is. It's actually a satellite swarm. You mentioned this earlier about the satellite swarms. So this is basically one satellite consisted of 5 autonomous separate satellites, and they're sent to space in the configuration like this. After we send them to space, for example, let's say that we know about this certain cloud on 800 kilometers altitude. So we send the aggregator a bit above this orbit. So we send it above the cloud. We open the satellites, and this massive net comes out of the satellite. The net can be made of these really novel nanofiber or graphene fiber materials, which are really strong, extremely strong. And I think right now they're developing a material which is stronger than graphene, which is incredible. And we think that you can achieve fairly big net with materials like this. I think we can get something like 3 square kilometers big net. It's quite big, and it can weigh up to 15 kilograms. So we open the configuration, the net spreads, and then we decrease the speed of the whole configuration. So it goes in front of the cloud and is moving slightly slower than the debris. So the debris will start to enter the net, okay? And after the cloud is clean, or the orbit is clean, or the net is full, I don't think we can fill this up, but let's hope that we don't have to. After the net is full, the 4 peripheral satellites close, so they interlock the net, and the retainer at the front continues to control the whole configuration. Afterwards, what happens with the package is something that we can imply forced re-entry in the Earth atmosphere. We can burn this up, or we can store it in gray orbit, as I mentioned earlier. But we have to be quick. After we detect the cloud of debris, we have to act fast, because due to natural reasons, this cloud will not be moving together all the time. It will slowly spread around Earth, because these parts are all the debris are spinning with different speeds, the different mass and slightly different velocity vectors, so they will spread, and they will be much harder to get. So this is why we're thinking of using the air launch system. That means that we need to think about not launching the satellites from these massive rockets and to have these dedicated spaceports. We don't have this in Bulgaria. And if we depend on having a base like NASA or Cosmos, we'll probably will not be able to launch satellite in the next 200 years. So we're thinking about using airplane to go to higher altitude, and the military airplane fighters, they can go to maybe 20 kilometers, and they can move really fast. So you can afford having much smaller carrier rocket, because the first few kilometers are actually the toughest to penetrate. Let's say. You need a lot of fuel, and if you use an airplane, you can just save this. Okay. And countries like Bulgaria, I don't know if in your country there is a spaceport, but I'm sure there are planes, so we can all enjoy launching satellites with this system. This is an example for the Russian Microspace 2 project. It can carry up to 40 kilograms of a satellite, and it could shoot the satellite to about 1,000 kilometers altitude, which is, it's okay for us. It's good enough. This is the last project. It's an American project. A bit heavier satellite. It can carry 45 kilograms, and again 1,000 kilometers altitude. And just another example, another American project. And this is actually a civil airplane. I think it goes up to 12 kilometers, something like that, high. And then the rocket shoots. This is the Go Launcher project with the same parameters as the last one. So this is how we imagine to achieve to face this problem with solution which is maybe not that expensive. It's not that cheap, but it could be more expensive. So like everything in life, nothing's perfect. Everything carries certain risk. So I'm going to list some of the risks we think about. First one is low efficiency and accuracy of the debris detection. We need extreme accuracy. We cannot afford to have a mistake with 100 meters or 10 meters maybe. We have to be able to define the cloud, and we have to be able to see what type of debris we have, because sometimes if you have like a fuel tank in the debris with some fuel still remaining, it could blow up your net, and it could be worse. Then the complex mission planning for the aggregators flight. If we don't have good data, the mission planning will be a disaster. And I think if we manage to, handle the first problem, this will be next the result list. So we have also difficult and risky deployment and closing of the net. We're talking about massive net, and when you have these peripheral satellites flying on different altitudes, they have to move with different speeds. So we have to compensate for this in some way, and we maybe need a lot of fuel, and the problems will go on. Possible net breakage. This is something that I can't even imagine. If we get a lot of debris together and then the net breaks, imagine having the debris again, freely orbiting the Earth, and also a gigantic net just wiping everything in the way uncontrollably. we'll probably need even bigger net to get this one. I don't know what will happen, but it will be a disaster. So also we are considering the unpredictable behavior of the captured debris. So we can have something that explodes or something that spins too fast and rolls up our net, and then we have to go home. And I'm sure that the list will be continuous if we talk about this a bit more. But we're still developing this idea. This is the pre-idea, let's say, and we'll try to resolve some of these problems and risks, and we'll see what will happen. Yeah, thank you.